Hello everyone, welcome to this course again. So in this lecture we are going to talk about pretraining strategies. Last lecture we covered transformer, different blocks of a transformer model, right? We also talked about word-to-way glove models, which are pre-trained word embedding methods, right? And we will see the overall arena of pre-training with transformer, and then we'll also see how the how the paradigm of pre-training actually changed from pre-trained word embedding to pre-trained language model. Let's look at the pre-training strategy. Okay, so while discussing this, let us start with this famous quote which we already mentioned earlier in the distributional semantics chapter, in the word embedding chapter, that we shall know a word by the company it keeps, right? So the same person modified the quote later on, and then he said that the complete meaning of a word is always contextual. Okay, this is always contextual, and no study of meaning apart from a complete context can be taken seriously. Okay, and this is essentially the foundation behind building the pre-training strategies. Okay, this is an example. I record the record, right? If you look at these the two positions of the word record, right, the meanings are completely different. Now if you use a word-to-way kind of method or a glove kind of method, which basically produce pre-trained embeddings, right, you will get same embedding for these two positions of record, right, but the meanings are different. Okay, let's take another example. A bat flew out of the cave. He hit the ball with a bat. Again, here the two words bat, the two positions of the word bat, the two contexts of the word bat are different, right? If you use the same embedding to represent this, you will not be able to do the proper processing of it, right? So what we will do here, we will produce embeddings, word embeddings, which are going to be contextualized, meaning depending on the context, the embedding will change. For example, here, let's say for the word bat, you will get one embedding. For the word bat here, you get another embedding, which are different. Okay, how do you do this? The first approach which was proposed, which is not a transformer based approach, this was proposed in 2018, is called ELMo, right? Deep contextualized word representation, right? This was done by mostly by LNAI team, and some folks from this university also, right? One of them is a very good friend of mine. So the idea behind the ELMo method is as follows. So ELMo is a non-transformer based approach. There is no concept of transformer. Transformers was introduced in 2017. Around the same time it was introduced, 2018, right? So ELMo stands for embedding from language models. What it does, it essentially relies on RNNs, right? Can be LSTM, can be GRU, right? RNNs. And what it does, it essentially processes a sequence, right? When you process a sequence using RNN, each of the hidden states, which correspond to basically the tokens, right? These hidden states will basically be used as embeddings, right? Let's say I am going to school. This is my RNN. Okay. In RNN, what do we learn? We learn the weight matrix W, right? There are how many matrices are there in general? Generally, there are three matrices. One is a matrix between layers, right? WH. Another is this WE, which corresponds to the input, and other is this U, which basically projects it to the output space, right? For the time being, you just assume that there's only one matrix, which is WH. Okay, so you have an RNN, a fixed length RNN, right? and then what you do, you pass one training instance, okay, and you train this RNN using language model objective, next word prediction, right? You pass one sequence, you predict the first position of the sequence, second position, third position, fourth position, and so on and so forth, right? You do backprop and then you update WH, right? Then again you pass another sequence, you update this, and so on and so forth. Now think about it, what is happening here? So the claim is that the hidden state will act as an embedding. The hidden state here, let's say this hidden state will act as an embedding for the word to, right? Now you may wonder how would it be possible, because there are so many sequences, there's only one RNN, right? So let's think of a dictionary, right, where every row indicates an embedding of a particular token, right? Let's assume that this is a word level token, right? Not a character level, word level tokenization. So there is an entry I, and this is the vector. Entry j, this is a vector, and so on and so forth. And let's assume that this matrix is initially randomly initialized. Okay. Now, when you start this RNN, you need to feed the input, right? This input is taken. This input is fetched from the dictionary. So the so when the input is I, you basically fetch the corresponding embedding vector from the dictionary and you feed it as an input, right? To start with. Then you train the model. Let's say you take one instance, you train the model, your hidden states are updated, right? The hidden state corresponding to the word I is also updated, right? So when the training process is done, you take that hidden state and you replace the previous embedding of I by this hidden state. Done. Another instance, another training sentence comes in. You use the same RNN. Okay, let's say this is C is eating a pizza. Okay, so what you do first? How do you initialize this? You take the embedding of C from the dictionary, is, right, eating, and so on and so forth, right? You already have this weight matrix which came from the previous iteration. You again update it. You update the hidden states, and the corresponding dictionary is updated. You keep on doing this thing with all these instances. Now you can say that, you know, I will train the model using batches. That is also possible. You take a batch and then you do this update, or let's say per instance you basically update this RNN. Okay, so this is a language model objective based RNN model. There is no task involved so far. Now, so this is now what you do. So this is your first RNN, which is a language model objective based RNN. When all these things are done, you freeze this RNN. When you freeze this, what does it mean? It means all the embeddings are freezed, right? And now let's say you are interested in doing some task. Okay, and let's say you have some task specific data. You have some task specific data which you want to use to train the model further. Right? Some sort of fine tuning. Okay, so on top of this, you apply another RNN, which will be responsible for doing this task. And let's say the task is sentiment analysis. Okay, this is sentiment analysis. So this is frozen. It is frozen means the hidden states are coming from this, the first layer. So given the task specific input, all the tokens embeddings are coming from this layer, which are frozen, right? And here in the second layer, you have another weight matrix WH dash, which corresponds to that layer, and you have the task. You produce the some output. There is some error, right? You backprop and you update the weights. The task specific weights are updated. So during the inference time, let's say you are given a sentence, right? What do you do first? You are given a sentence, then you first retrieve. Now remember, there are two layers. Don't forget, there are two layers. The first layer is a language model layer. The second layer is a task specific layer. right? During the inference time, what you do? During the inference time, you feed here, right? You basically feed here. The bottom layer, the corresponding weight WH is already stored. It has already been learned, right? So let's say you are feeding a new sentence. Let's say Akshay is a great cricket player. Okay. So what you do? So this is my first layer. Okay. So you feed the input, the input vector of Akshay from the dictionary, right? You multiply this with the weight WH, right? It will, and then Akshay is. Then you also have this is embedding for the word is. This and the previous hidden state will basically be used to generate the next hidden state, right? And so on and so forth. You roll out. Okay. When you roll out, now let's look at the current hidden states now. Now these hidden states, the current hidden states of the bottom layer are very different from the hidden states which are stored earlier, because these are multiplied by, these are basically functions of the weight matrix, right? And this is contextual. Why this is contextual? Because the word great is now dependent on the previous word, which is Akshay is. Okay, maybe the word great was used in some other context, but in this context, this is a function of the previous words. Clear? So the bottom layer will produce some hidden states, right? Now these hidden states will be moved to the task specific layer, and the task specific layer, we already know the corresponding weight which was learned earlier. That will be used to predict the task. Okay. Now there are some changes here and there. What I mentioned is a very high level overview of this. Let's look at the changes. But the bottom line story should be clear, right? There are two layers. One layer is responsible for language model objective. The top layer is responsible for tasks, right? Here you store the hidden states as embeddings of the tokens, right? And then the embeddings will be changed when you apply for a specific context. It will change. Okay. Okay. RNN is not a very great approach. I mean, unidirectional RNN is not a very great approach because it only scans from left to right, right? As you understand, for a language model objective, why do we just need to scan? Because I want to process the entire sentence. So along with the left to right RNN, I will also use a right to left RNN to process the entire sentence. Now left to right RNN will basically predict the next word from left to right. Right to left RNN will basically predict the word from right to left. Okay. Now, I mean, there are two ways to essentially do this thing. Let's say if you have access to only a left to right RNN, not an right to left RNN, what we can do, you can just rotate the sentence, right? Let's say I'm going to school to going am I, and then you run a left to right RNN. Okay. In fact, what they did, they used a stacked RNN. There are two layers. Now this RNN that I'm talking about is a language model RNN, the bottom RNN that I mentioned earlier. So the bottom RNN was essentially a stacked RNN. There are two layers, right? So you see here, this is one RNN called the forward language model. There are two layers, layer 1 and layer 2, right? And this is the backward backward RNN. Here also there are two layers, layer 1 and layer 2, right? A cute puppy and a cute puppy. Okay, left to right and right to left. Then what is going to be my final hidden state, which I am going to store into the dictionary? The final hidden state corresponding to the word cute, right, can be either the concatenation of this and this, right, or it can be, let's say, only the top layers, this plus this. Plus means concatenation, right? There can be multiple ways of combining this. Let's look at it here. So you have a left to right RNN. Okay, look at this equation very carefully. Okay, so this is a language model objective here. So you have You are given a sequence of tokens T1, T2, dot 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 Tk minus 1. You are predicting Tk. What is this one? This is essentially the LSTM, I mean the RNN parameter, which is WH, right? All the other parameters, meaning the, let's say WE, right? All the other parameters in the RNN will remain the same. What is WE? WE is the parameter corresponding to the input, right? In this case, this is theta x. This will remain the same in the forward LSTM and the backward LSTM. Okay, all the other parameters. What is this theta s? What is this theta s? Theta s, the s is the u. Okay, the softmax parameter. This will also remain the same in forward and backward. So the only parameter which is going to change is the WH. Okay, so then you essentially add these two. Look at here. This is, I think, better way to represent it. So for every token k, you got one representation from the forward layer and one representation from the backward layer, right? Either you just concatenate them. So what they argued is that instead of taking this embedding, this embedding, this embedding, and this embedding, instead of taking 4 embeddings for a particular token, we will only use the top layers, not the bottom layers. Why bottom layers are not that interesting? So after the top layers, we have this U matrix, right, and the softmax. So when you do backprop, right, this layer will be affected more compared to the bottom layer. So task specific weight is just above the top layer. I'll only use the top layers, and the corresponding vectors will be fetched and concatenated. Okay. In fact, what they said is that instead of doing this, you can also add some parameters. So along with this, which is the combination of backward and forward, you add a parameter. Now this parameter is a layer specific parameter. Look at here, layer J ranges from 0 to L, and there are two parameters. One is this gamma, one is this S, right? Now this S corresponds to a specific layer and this gamma corresponds to a specific task. What does it mean? It means that when you, on top of this language model layer, when you apply a task specific layer, right? I mentioned earlier that the language model is going to be frozen, right? What they said is that instead of freezing it completely, you add some parameters which will be dependent on the task. Okay, this hidden state will not be updated, but the parameters will be updated. Parameters corresponding to the hidden states will be updated. It means during the inference time, when you feed one specific instance for that specific task, you basically fetch S and gamma. You see, because these parameters are already learned. So now your hidden states are a little bit dependent on the parameters of the task. Now if you want, you can discard this dependency. You can just remove this task specific parameters, only use the hidden state, right? But if you feel that, okay, some dependency should be there, you can use this, right? Some other properties of this: ELMo uses token level representation. This token is essentially character level token, not a word level token. Okay, so for that they used a CNN, right, 2048 character CNN conv layer, and then some linear projection and so on and so forth. Because character level encoding always helps you overcome the UNK kind of problem, right? UNC token problem. Okay, let's look at the result very quickly. So ELMo was one of the first large scale models. Okay, million size models. I think 90 million or something like that. I forget the exact size. It was tested on different tasks, question answering tasks, squad question answering tasks. The squad dataset was proposed by Stanford again in 2017, 2018, during that time. We'll talk about it later. Another task was natural language inference task, right? Semantic role leveling task, co-reference resolution task, named entity recognition task, sentiment analysis task. This SST5 is a very famous data set, right? And if you look at the results, there is always an increase, right? In fact, in some cases, increase is significant, quite significant compared to the other models. Okay, this is the previous SOTA output, right? State-of-the-art model, and this is ELMo. In fact, you can use ELMo to initiate transformer, right? In a transformer also, you need to feed embeddings, right? Instead of using what to wake, you can essentially use ELMo's representation. Okay, so this is all about ELMo. So ELMo is yet another word embedding technique, but contextual, dynamic, unlike word to wake glove, which was static, right? Context independent. So we have been talking about pretrained word vectors. In pretrained word vectors, your embedding layer is frozen, right? And your task specific layer is essentially something that you are interested in. Okay, now this part is pretrained. Model is not pretrained. The entire model is not pretrained. Only the inputs are pretrained, right? Now from pretrained word vectors, we are moving to pretrained models. In the pretrained model, all the parameters are pretrained, right? What are the parameters in a transformer model? The parameters are the parameters corresponding to the attentions, right? Parameters corresponding to feed-forward network. All of them are pretrained, right? Then for a specific task, you then fine-tune it. Okay. So let's look at. So there are three kinds of pretrainings that we are interested in, right? Depending on which part of the transformer we are interested, right? Transformer, there is an encoder block, there's a decoder block. So one type of pretraining only considers the decoder part of the transformer. Okay, so all these GPT series models, they are only decoder only models, decoder-based models, right? They do not consider the encoder part. Therefore, this cross attention is not there. Okay. The other type of models are encoder-only models, where we only look at the encoder part of it, we forget the decoder part, and then we'll pretrain the encoder model. But right, Albert, Robota, all these models are encoder-only model, and then the normal structure, which is the encoder-decoder kind of model, the transformer, the actual transformer model, this can also be used for pretraining, right? So GPT comes here, BERT series model comes here, and T5, right? Another model is called BERT, B-A-R-T. These are all basically encoder-decoder models. Okay. So let's look at this BERT, B-E-R-T model proposed by Google. Okay. So BERT stands for bidirectional encoder representations from transformer, and this is the paper. So now we have only the encoder part of the transformer model, only the encoder part, and now we are pretraining this encoder part. Okay, encoder part. The beauty of the encoder part is that there is no masked self attention. This is unmasked self attention, meaning all the tokens, each of the tokens can attend to all the other tokens in the sequence, right? So it is some sort of bidirectional in nature, because you can scan from left to right, right to left, and whatever. So in BERT, when you pre-train, what we do, we essentially, now for pre-training, what is my objective? Because I don't have any task specific data, I only have access to raw corpus, right? Raw corpus, raw sentences. What is going to be my objective? So in this paper, they came up with an objective called mask language model, MLM. Now this is a self-supervised approach, not an unsupervised approach, because there is some gradient flow. Self-supervised approach, you don't need any label data, right? So what you do in BERT, in the encoder part, is that you feed a sentence, right? And you mask some of the tokens of the sentence. and let's say for the time being the tokens are words. You mask some of the tokens and you let the model predict those tokens. Okay. Now there are so many questions. For example, which tokens I should mask, how many tokens I should mask, right, and so on and so forth. So these are all empirical questions, and what they showed is that 50% masking is enough. So you mask 15% of tokens present in the training set, right? But when you mask it in three different ways. Okay. Out of this 15%, 80% cases, right? You basically just mask that token, right? So what does it mean by masking a token? So they introduced a new token called mask, right? A new token called mask. When you feed, right, you replace a word, you replace a token by mask. Okay, and at that position corresponding to the final output, you predict what is going to be the actual word at the place of mask. Okay, so 80% time you mask some of the tokens, 10% times you replace that token by another token. Let's say the sentence is like going to the park, you replace the word park by store, and you let the model predict the word park, right? This is some sort of corruption. You do some sort of corruption and you let the model predict the actual word, right? And 10% of time you don't do any change, but still you let the model predict it. Your input is like going to the park, right? You let the model predict the word park. Why this is important? Why this is important? This is important because if you only teach the model to predict the mask token, the model will basically start predicting the actual tokens. So sometimes you also need to, tell the model that look, I mean, you are learning this mask output, but you also need to understand what is there in the other tokens. Okay. So why 15%? Why not 50%? If you mask 50% of the tokens, right, most of the context will be destructed. Your context, you also need some context, right? The context will be gone, right? So they empirically tested that 15% is a good number. 15% of an 1 billion or a 10 billion size token is good enough. This is my sentence. Let's say like going to the park, right? You feed this, you replace this by mask, okay, and you want the model to predict like going to the park. So your error is only computed here, not at the other tokens, other token positions. This is very important, right? Now this is not all about BERT. I am coming to the other parts of it. So mask language modeling is clear. So one task is this mask language prediction. Okay, mask language model. So they use two tasks. One is this mask language prediction, and the second is next sentence prediction. What is next sentence prediction? You give two sentences, right? You have this corpus. You know which sentences are there side by side. You know the two consecutive sentences. You take two sentences, W1 and W2, and you let the model predict whether W2 will follow W1 or not. So for the training data, what you do, you take those pairs of sentences which actually appear side by side, right, as your positive samples, and as your negative sample, you do random shuffling, right, and you basically take those pairs which do not appear side by side. Let's say I enjoy reading the book, right? I finished the novel, these two sentences appear side by side, so the label is yes, otherwise the label is no, right? So these are two tasks, and we will do these two tasks simultaneously, meaning let's say the input is I enjoyed reading the mask, okay, and how to separate these two sequences? This is sequence 1, sequence 2, the novel was great, right? We separate them using another token called ACP, separator. The separator is a new token, like a mask token, right? And again you may have a separator here, right? So you introduce two new tokens. Along with this, we introduce another token called the CLS token, and this is prepended with the sequence. This stands for classification. Okay, so you feed this entire thing to the encoder block, right? What is the need of this CLS token? Now let me first tell you what will happen after this. So the model will predict the vectors, right, at the end, right? Vector corresponding to CLS, vector corresponding to I, and so on and so forth. And it will also try to predict this mask word. On top of this CLS, I will use a task specific head, meaning basically a linear layer U, right, which will project it into two classes, yes or no. Okay, if two sentences are sequential, then it will predict yes, otherwise no. There are two losses. One loss is here, another loss is here, mask, and those two losses will be backpropagated, right? Now my question is, why do we need this CLS token? Can't we just take the embeddings of all these tokens and then concatenate it and then pass it through a linear layer followed by nonlinearity? Okay, what he's saying that we can't take the concatenation because we don't essentially know this one, the actual mask token, right? Okay, that's fine. Then we just ignore the mask token and somehow combine the other tokens. So the other tokens are good enough. Only 15% are masked. Why the CLS token? So remember, CLS token also acts as a normal token, meaning CLS also attends to all the other tokens. In the self-attention part, it has attended to all the other tokens. So CLS has information about all the tokens, right? But CLS token is a token which doesn't indicate any meaning present in the sentence, because this is not a part of the sentence at all. You may argue that why do I need a classification layer on top of CLS? I can have a classification layer on top of I or on top of read. They have also attended to all the other tokens, right? But they themselves have some meanings. A CLS is a token which is not present in the sequence at all. So it is not biased. That token is not biased. The CLS token is not biased to any of the other tokens present in the sequence, whereas the token I is biased towards itself. Attention score would be high, right? In fact, there is another plus point, behind using CLS for the classification. How many weights you are incorporating here? Apart from the the normal encoder weights, self-attention feed forward weights, these are already there in the encoder. for this classification, how many weights you are incorporating? Parameters you are incorporating. Only this part, right? Only u. And what is the size of u? If the vector size is 512, this is 512 into 2. Right? Instead of this, if we had a concatenation of tokens, this is going to be bigger. Right? The parameter size can also be decreased. Okay? Now, this error, which is the task specific error, will get back propagated end to end. Right? The error related to this mask token and the error which is there on top of this CLS token, those two errors will be back propagated end to end, and all the encoder blocks will be updated. Okay. Now this is encoder. You can use this encoder block for word embeddings also. Like ELMo, you can use BERT for contextual word embeddings. Okay. All right. So this is the graphical depiction. Look at here. E0, E1, E2, E3, E4. Basically, you want to E4, right? From this to this is one sequence. From this to this is another sequence. This to this is another sequence, right? My dog is cute. He likes playing, right? You have a positional encoding, right? So in here they introduce another encoding called the segment encoding. Segment encoding is just indicating whether this is this token comes from the first sentence or the second sentence, right? So segment, this is A and this is B. Right? So positional encoding, segment encoding. Then from that you also have this token normal token encoding. This can come from ELMo, can come from word to wake, and so on and so forth. And then you have this CLS prepended ACP separator, and so on and so forth. Now this is my input sequence. You mask some of them and you feed. So this is the training details. They used 2.5 billion Wikipedia corpus, another book corpus consisting of 800 million words. They tested two different variations of BERT base consisting of only 12 layers of encoder, and BERT large consists of 24 layers of encoder with different hidden state size and different multi-headed attention. 12 head, 16 head, right, and so on and so forth. There are other epochs and so on. The other details are also mentioned here. Okay, now if I ask you, can we use BERT for a downstream task, and let's say the downstream task is question answering. Okay, what is the question answering task? You are given a question queue. Okay, and let's say who played the role of Bikram Rathore in Jawan. Okay, this is the question, and this is the passage. You have a passage where all these things are written, and somewhere in this passage it is written that the role of Bikram Rathore, right, was played by Shah Rukh Khan, right? This is the passage, and your task would be to essentially retrieve this information from the passage. Now tell me, how do we use BERT for this kind of task? Okay, this is a typical closed book kind of question answering task where you are given. Now there are so many data sets. Squad is one data set, right? There are other data sets like Quark, right? Hotspot QA. There are so many data sets available. Some data sets look like this. Some data sets basically are conversational data sets where you have conversation, you ask a question, and you retrieve answer from the conversation. How do we use this the BERT model to solve this kind of task? What do you think? The BERT model is already pre-trained using masked language model. right? Now, when you fine tune the model for this task, you already have some training data where the question and the corresponding passage is the input and the output is the specific token, right? So what you do here in the BERT model, this is BERT, you adapt to this model for a specific task. This is one such task, okay? So during training, you feed question Q, right? Separator and the passage P, separator, okay? And you have CLS, okay? So you have different tokens here. You have token, let's say token T1, token T2, T3, dot, right? So T60 and so on and so forth. Then what you do, you add a classification layer on top of every token. In fact, you add two classification layers on top of every token, right? One classification layer will be responsible for, I mean, you can think of this specific phrase as a span, right? So this is start of a span, this is end of a span. So here in this passage, there is this word called Shahrukh Khan, right? And the corresponding embedding of Sa, corresponding embedding of Rook, corresponding embedding of Khan will also be present here, right? You maintain two different classification heads. One classification head will basically keep track of the beginning of the span, and other will keep track of the end of the span. Let's say you have C1, let's say CB, CE, okay? So CB for all these tokens will be 0, 0, 0, 0, 0, 0 during training, right? And for the word Sa, right, CB is going to be 1 and CE will be 0. And then the Rook will be 0, 0, Khan will be 0 and 1. And the remaining will be 0, 0, 0. This is my ground truth data. I want the model to predict these labels, right? Now you feed the input to the model will produce the embeddings, right? And those embeddings will be fed to the classification layers. Classification layers will essentially produce some probabilities. There are two probabilities. One is the probability that the current token is act as a beginning, and the current token acts as an end, right? So my hope will be that the token corresponds to Sa is going to be the PB for the token Sa is going to be 10 to 1, that tends to 1, and the PE corresponds to Khan tends to 1, right? If it doesn't happen, then there's a loss, and that loss gets back propagated, right? Task specific layers, meaning these two layers, right? These two layers will be mostly updated, and the other pre-trained layers can also be updated. Okay, so the model is now adhered to a specific task. When a test sentence comes in, the test question and the passage, what do? You use this pre-trained model, pre-train followed by fine-tune, whatever the model that is there, right? You pass the sequence, right? It will produce B and PE for all these tokens, and our task would be to maximize what? The task would be to basically figure out two such positions such that PB times PE will be maximum. Now think about it. For every token, you have two probabilities, PB, PE, right? There are so many possible combinations are there, right? PB times PE, so PB1 times PE2, right? PB3 times PE1 and so on and so forth. All these combinations are possible. Which combination I will take? I will take that combination where number one, the end token I mean, let's say you have chosen I and J as two different positions, right? And PB comes from I and PE comes from PE comes from J. J should always be greater than I, of course, right? The end token should come after the beginning token, right? This is the first condition, or whatever, greater than equals to, because only one token can also be possible. Okay, and then considering this condition, then I want to maximize this probability, PB times PE. Now you may ask that in a passage there are multiple appearances of the word Shahrukh Khan, so which one I will consider, right? So generally you consider the beginning, the first appearance of the word Shahrukh Khan. Okay, so in this way you can essentially use a pre-trained BERT model for a downstream task like question answering task, which apparently looks very different from the pre-training objective, right? Now this is all about BERT. It was tested across multiple tasks, right? This question answering task, natural language inference task. Remember, for each of these tasks you need to adapt your model accordingly, right? This is this Schola benchmark, which is a corpus of linguistic acceptability. Is basically indicates whether sentence is grammatically correct or not, right? STS benchmark, SPET, RET benchmark, and so on and so forth. And it showed that BERT large significantly improves the tasks, right, compared to the other baselines, which was SOTA at that time. It also beat the GPT-1 model. Okay, BERT had been one of the state-of-the-art models till 2020, and following BERT, there were approaches like DBERT, RoBERT, right, Tiny BERT, where people started squeezing the model, right, making the model tiny. Then this RoBERT paper says that the BERT model is under-trained. You need to train them, more and more, and so on and so forth. There are papers where people essentially feed a lot of training data across multiple tasks. People also showed when you keep on adding new tasks, how the model, whether the model will be generalized or not, and so on and so forth, right? So this is one direction of research. I will not go into the details of the follow-up of BERT, but I will strongly suggest you guys to read those papers. At least use those models for your projects. Okay. With this, I stop here, and in the next lecture, we will try to address the other types of pre-trainings like GPD and T5. Yeah? Thank you.